This is a video about electric forces. The electric force is also called Coulombs Law. We can find the masses of protons, neutrons, and electrons in the table of information. Now, in the world of electric forces, the most important unit is the Coulomb. The Coulomb. Just like in the world of gravitational forces, the most important unit was a kilogram for mass. In the electric world, the most important unit is Coulomb for charge. So we're in a new world of electric forces that involve charges, as opposed to when we were looking at the world of gravity that involved masses, and the main unit there for masses is kilograms. The smallest unit of charge in this new world is this value here, 1.6 times 10 to the minus 19th coulombs. Now, that's the smallest unit of charge that we can have. Each electron and each proton has the exact value of 1.60 times 10 to the minus 19 coulombs. Now, all charges are some integer multiple of that value. That value, E, that 1.60 times 10 to the minus 19 coulombs, again, being the smallest unit of charge, means that any other charges have to be some integer multiple of that value. Because of that, we call the charges on electrons, protons, and all other charged particles quantized, because they're integer multiples of that smallest unit. Now, let's say, for example, we had 1 coulomb of charge. Let's figure out how many electrons are in 1 coulomb of charge. So, if we've got 1 coulomb charge, their net charge would be negative 1.00 coulombs, because they would be negative. We would divide that by the number 1.6 times 10 to the minus 19th charges per electron, because we know, once again, each electron has to have that charge. The Coulomb units canceled, and we end up with 6.25 times 10 to the 18th electrons. That's a lot of electrons for just 1 coulomb of charge. So 1 coulomb charge is actually a very, very large value. Now, this is Coulomb's law the way it is written in your equation sheet. You should know that this part of it we also call K, the 1 over 4 pi epsilon naught. That value of epsilon naught is also in your table of information. It's this value here. 8.85 times 10 to the minus 12th Coulomb squared per Newton meter squared. Now, again, that's a constant. Don't have to memorize it. It's on the table of information. So when we plug the value K, which is 1 over 4 pi epsilon naught, into Coulomb's law, we get 9.0 times 10 to the 9th newtons meter squared per coulomb squared. So basically what we're doing is we're taking this value of K and plugging it into here, and that's the main value we should probably be using most of the time. And again, that value is available in your table of information. So the other important things to notice about Coulomb's law is that we need to have 2 charges, and we need to know the distance between those 2 charges. Before we look at Coulomb's law some more, let's go back and look at the world of gravity. So again, there's Coulomb's law. Let's compare the gravitational world to the electrical world, starting first with the gravitational world. Remember this equation? This is the equation of the gravitational world that relates the force between any two masses and the distance between them. And that's the universal gravitational constant right there, that big G. So in the world of gravitational forces, in order for an object to experience a force, it must have mass. So the world of gravitational forces, the most important property is mass. If an object has mass, then it can potentially experience a force. So let's look at these two masses, M1 and M2, with M2 being larger, and they're separated by some distance r. Remember that the law of gravitational force says that M1 is going to be attracted to M2 by some force 2 onto 1. So some gravitational force of object 2 onto 1, and it points to the right. Similarly, object 2 is attracted to object M1 by another force, which we'll call F1 onto 2. So it's the force of object 1 onto object 2 that attracts it to the left. So what's important to remember here is that those two forces, because of Newton's third law, are equal and opposite. So if we add them together, if we add these two forces together, we should get a value of 0. So what's that relationship between those two forces? Well, from Newton's third law, they're equal but opposite. And which one has a greater acceleration? Well, if we remember back when we looked at Newton's second law, remember Newton's second law said the sum of the forces equals a mass times acceleration. So because the acceleration for the smaller object is the force divided by the mass, this mass M1 will have the greater acceleration because it's got a smaller mass. And the smaller mass in the denominator makes the acceleration a really, really big number. Remember, these two forces are going to be the same. What's different between the two masses is that M1 is smaller, so it's going to have the greater acceleration. So let's see how these principles apply themselves in our new electrical world. In our electrical world, in order to experience a force, an object must have charge. So notice that the equation Coulombs Law is really, really similar to the universal gravitational force equation. They both involve two objects, and knowing the values of the quantities of two objects and the distance between them. So if we look at two charges, this time an object with a negative charge and an object with a positive charge, just like in the gravitational world, they will experience attractive forces. So negative Q1, this charge here, negative Q1, is going to experience a force of object 2 onto 1 to the right, just like in our mass world. And likewise, object 2 is going to experience a force of 1 onto 2. And it's in the opposite direction. So just like in the gravitational world, we're going to experience forces that are equal but opposite. And adding those two forces would also give us 0. Those two forces are indeed equal and opposite. And Newton's third law still applies, as does Newton's second law. If one of these objects has a lower mass and they both experience the same force, then whichever object has a lower mass is going to experience the greater acceleration, just like in the mass world. Now, what's different about the electrical world is we could have two objects with the same charge, and because of that, we can actually get what are called repulsive forces. So these would be repulsive forces, whereas these would be attractive forces. So gravitational, at least in the classic sense, gravity only attracts. In the electrical world, if we got two opposite charges, we could get those two charges to attract. But if we've got the same charge, two positive charges, for example, they will actually repel. So this charge here, Q1, is experiencing a force of 2 onto 1 to the left, whereas object 2, or charge Q2, is experiencing a force of object 1 onto 2 to the right. But once again, these forces are equal but opposite. And in the same sense, they will also accelerate. They will accelerate just like they did in the mass world. All right. Note that an object can have both charge and mass. So it's actually possible for an object to experience a gravitational force and an electrical force. But most of the time when we deal with charges, their masses are so small that we ignore the gravitational forces between them. Okay, now let's say we've got an electron and a proton and they're 0.0050 meters apart. Let's find out what forces and accelerations they experience. And let's also draw force diagrams and motion maps. So essentially, let's go back to the force toolkit. So let's look at the proton first. So the proton, let's say that up is positive and to the right is positive. It's experiencing a force of the electron onto the proton to the right. So in that case, it's accelerating to the right. So the velocities are picking up speed to the right. In our case, we'll consider this acceleration constant. We'll go next to Newton's second law and then write out the forces that apply to just that object, to just this proton. There's only one force, and that's the force of the electron onto the proton. The mass that we're looking at is the proton mass, and this would be the acceleration of the proton. Now, this force is not being provided by gravity. It's being provided by Coulombs Law, by electrical forces. So that means we're going to have to apply Coulombs Law. So there's Coulombs Law written into Newton's second law. We're setting it equal, once again, to the mass of the proton times the acceleration of the proton. So let's put in the charges for both the electron and the proton. So there's the electron charge and the proton charge. Notice I left the negative and positives out for the time being. We'll talk more about the positives and negatives charges in class. But what's more important right now is to realize what direction this force of the electron onto the proton is. And it's to the right. So we plugged in our values, that we took the distance between them and squared, set that equal to the mass times acceleration of the proton, and we find is the force that the electron is pulling the proton with is 9.22 times 10 to the minus 24th newtons. And if we want to solve that for the acceleration, we divide both sides by the mass. Well, first we have to find the mass. Again, we can find this mass from the table of information. It's probably a good idea for you to familiarize yourself with the table of information and find out where that value is. That's a value of the mass of the proton. Now let's solve for the acceleration of the proton. So we have to divide both sides by the mass of the proton, just like that, and we get a value of 5,520 meters per second squared. That's acceleration, and it's going to the right because our force diagram says it's got to be going to the right. Now, let's look at the force that the proton pulls the electron with. So in this case, it's still positive upward and to the right. That's our convention. But the electron is being pulled to the left by the proton, so we'll show that in our force diagram that it is indeed being pulled to the left. Our velocities start with, it starts with no velocity and increases velocity to the left, so that means our accelerations are constant and to the left. Again, we write down Newton's second law to maximize our credit. Then we plug in the actual forces into Newton's second law. So there's our Newton's second law equation. We're plugging in the negative force of the proton onto the electron, and that equals the mass of the electron times the acceleration of the electron. So this force here again is Coulombs Law. We're in the electrical world, and we need to plug that equation in, or plug the values into this equation. So our values, once again, the charge of an electron and the charge of a proton, these also are available on your table in your table of information. The problem tells us that the distance between them is 0.0050 meters squared. So, as should be expected, we get the same force, but in the opposite direction. 9.22 times 10 to the minus 24 newtons, and that equals the mass of the electron times acceleration of the electron. This is the mass of the electron. You can find that in the table of information. We'll divide both sides by the mass of the electron, and notice we get a significantly higher acceleration for the electron because it has a significantly smaller mass. Therefore, it's experiencing a greater acceleration, even though both objects had the same force. And again, it's important to notice what direction the object's moving in, and it's indeed moving to the left. So let's look at forces on a line. So what we have here is one charge, Q1. It's got a value of positive 3 microcoulombs. A microcoulomb is equal to 10 to the minus 6. On the left-hand side, there's a charge Q2. It's got a value of negative 4 microcoulombs, and it's 0.20 meters away from Q1. And then there's Q3 that's got a charge of negative 7 microcoulombs, and it's the distance between it and Q1 is 0.15 meters. So let's once again apply our force toolkit to this. So we'll call up positive and to the right positive. Now Q1 is being pulled by Q3 with a force of F3 onto 1. Similarly, force Q1 is being pulled by force Q2 with the force F2 onto the 1 to the left. So that's our complete force diagram there. Now, we don't quite know it yet, or we may not know it till we actually calculate the value of the force and the acceleration. But in this case, if we look at this, we notice that the positive 3 times the negative 7 is going to give us a larger value than the positive 3 times the negative 4 in Coulombs law. So I'm kind of jumping the gun a little bit here and showing you that the acceleration is going to be to the right. Many times in these problems, it's possible you may not know that till the problem is actually done. So you would have to wait for the motion map till you figure out the actual value of the acceleration and you know what direction it's in. So we write down Newton's second law. This time, Newton's second law has two forces. It's got a force of 2 onto 1, that's pulling it to the left, and another force, 3 onto 1. But we want to look at how those forces affect object number 1. So we're going to need to use Coulombs law twice. So the force of 2 onto 1, this will be the equation. Again, remember that's the value k. We take each charge, 4 times 10 to the minus 6, 3 times 10 to the minus 6 for these two charges, and divide it by the distance between them squared. So that's the force of 2 onto 1. Then let's look at the force 3 onto 1. Once again, we need the value k. The two charges, 3 times 10 to the minus 6, that charge, and 7 times 10 to the minus 6. Notice we left the negative signs out again. And divide it by the distance between them squared. So that'll give us two values, this value and this value. We take both of those values and we add them together. So this value gets negative 2.7 newtons. And this value gives 8.4 newtons, and that gives us a total force of 5.7 newtons to the right. So we were correct in assuming that the acceleration would be, or the net acceleration, I should say, should be to the right. And we could figure out that acceleration if we knew the mass of Q1. If we knew the mass of Q1, we could use Newton's second law, F is equal to the mass times acceleration. Take the acceleration, use this force here, 5.7 newtons, and divide it by the mass of Q1. The problem doesn't give it to us, but that's how we would find the acceleration for this particular problem.